Hey guys, Miss Marusik here, and in this video, we're going to talk about using Q and K values to determine the direction that a reaction would proceed in order to reach equilibrium. Now, we talked pretty extensively in our last video about the idea of a reaction quotient, that we can set our product concentrations over our reactant concentrations raised to their coefficients, and that ratio changes constantly during the reaction until we reach equilibrium. And at equilibrium, that ratio would stabilize out. The driving force in a reaction is that we are trying to get to equilibrium. We want that reaction quotient to equal the equilibrium constant. So if I know what the equilibrium constant is, and I know where my Q value is currently, then what we can do is ask ourselves, well, would I need to increase products or increase reactants in order to get those two ratios equal? So to start us off here, let's say our reaction quotient, our Q, is currently smaller than whatever the equilibrium constant, the K, is supposed to be. So what that means is that Q is too small. Well, think about the idea of products over reactants. If that ratio is too small, in order to increase Q, we would need to increase the numerator on top. We would need to increase the number of products. Now, in turn, if I'm increasing the number of products, that would end up decreasing the amount of reactants. The way we would talk about that shift of moving things is that we would say that the reaction would proceed towards the products side of the equation, or you could say it proceeds in the forward direction. Now, on the flip side, if the Q is currently bigger than the K, so the Q is too big, then in order to decrease that value, we would need to increase the denominator. The bottom, we would need to increase the amount of reactants. And so to get more reactants, we would need to decrease the amount of products. And so what we would say is that the reaction would proceed towards the reactant side, or we can say that it proceeds in the reverse direction. Now, to give us kind of a better idea of this kind of formula-wise, and even thinking about a little almost kind of number line we can use here to kind of give us an idea of how this works. Again, the whole idea is that I am trying to get Q to equal K. That is what I want. I want that reaction quotient to be equal to the equilibrium constant. And so if that ratio is not quite right, I'm going to shift things around in order to get those two equal to each other. So thinking on a number line here, let's say my Q was too small. Well, I want to get back to this point over here. So you notice that means I would want to shift in this direction. And I've kind of showed you here that would be a shift toward the product side of our equation. Now, to see this from a formula standpoint, if I am trying to get my too small Q to be bigger, then what I'm trying to do is to get that bigger, I want the products to go up. That would ensure that that gets bigger. But the kind of end result of that is that the reactants would end up also getting smaller as a result. So both of those actions together would help to increase that Q value so that it can equal K. Now, if my Q is too big, if it's on this farther side of a number line, then I want to shift back to where they're equal. So you can see going that direction, that would be a shift to the reactant side. And to think about this from a formula perspective, again, if my Q is too big and I'm trying to get it smaller, then that would mean I would want my numerator, my products, to decrease. But for products to decrease, the reactants would increase. And so the combo of those two together would help to lower that Q to where it can be equal to K. So again, we can see this from a numerical standpoint. And so that's what we're going to do on the next page. They actually give us some data for a reaction that was conducted. All right, so it says here that we have some questions with regards to the reaction of N2O4 gas in a reversible reaction with NO2 gas. And the first thing they want us to do is to write the formula for QC, which of course is also the formula for KC because they are both using that ratio of products over reactants. So here I would have my product on top. Now here we do see a coefficient being used. This is a coefficient of 2. 2, and so I would want to set that as an exponent here, over my reactant. Now my reactant only has a coefficient of 1, and so I can just simply leave that exponent blank. And so then what they have done here is they have run this experiment 3 times, starting at very different initial concentrations. And what they did is they measured the initial concentrations, and then once the reaction appeared to have stopped, it didn't really, it reached equilibrium because we see that two-way arrow there, it's reversible. But at equilibrium, once those concentrations stopped changing, they remeasured those concentrations. And so that's the data that you see here in the graph. For the first experiment, they have the initial concentrations and then the equilibrium concentrations. So to kind of point out what's happening here, let's look. We started for N2O4 with a molarity of 10. However, it went down to 9.79. So that was a decrease of 0.21. However, I noticed for the NO2, the molarity started at 1, but it went up to 1.42. So what I then did is I calculated the initial ratio of products over reactants, and then the final equilibrium expression, the equilibrium constant, again, products over reactants. It's the same ratio, it's just this time my numbers are what the concentrations are once I've reached equilibrium, but I calculate them in exactly the same way. So I see that my Q started at 0.1, but by the end of this I ended up at 0.21. And so then I did the same exact thing for the other 2 experiments. For experiment 2, I started with 5 molar of each. That got us to concentrations of 6.90 and 1.20. So here we had an increase of 1.9 and a decrease of 3.8. So again, I calculated my initial ratio and my final ratio. My initial ratio here ended up being 5, but my final ratio at equilibrium ended up being 0.21. We're going to talk about that here in a minute. Experiment 3, same idea. Here I started off with concentrations of 10 molar and 5 molar. I see that the 10 molar increased by 1.72 to give us 11.72. And the NO2 started at 5 molar and went down by 3.44 to 1.56. But again, I went and calculated my initial ratio here, which was 2.5, and my final ratio, which was 0.21. So it says some questions here. Let's kind of go through those together. It says, first off, for each experiment, compare the changes in concentrations of N2O4 to the changes in concentration of NO2. What do you notice about the relative magnitudes of these values? So to kind of look at these changes for a minute, I noticed that this went down by 0.21 and up by 0.42. So yes, one's going down and one's going up, but notice that this one's going down and this one's going up double the same amount. I see that here as well. We're going up by 1.9, but we're going down double of that at 3.8. Here I'm going up by 1.72, but I'm going down by double that of 3.44. So I always see that the change of NO2 is double the change of the N2O4, and it wants us to propose a reason why. Well, it has to do with coefficients, y'all. The change in NO2 is twice the magnitude of the change in N2O4 because I have a 2-to-1 molar or coefficient ratio between those. So now it asks, are the initial QC values for the 3 experiments relatively the same or fairly different? And then what about the equilibrium KC values? So I'm going to go look at my ratios we calculated over here, and I'm like, well, good gravy, these initial ratios are totally different from each other at 0.1 and 5 and 2.5. But then I look at those final KCs and I'm like, 0.21, 0.21, 0.21. So while the initial QC values were fairly different, those equilibrium KC values are relatively the same. Now, I will tell you this, if you take them out a few more decimal places, you might notice a little bit of difference between those because it's experimental data and it's not perfect, but basically they're the same value, which makes sense because this is all the same reaction and they were all conducted at the same temperature of 25 degrees Celsius, so therefore the ratio of products to reactants at equilibrium should always end at the same value. All right, so then it says, hey, In experiment 1, was the initial QC larger or smaller than the KC? So let's go back and look up here. Well, for experiment 1, my QC was 0.1, my final K was 0.21, so I'm starting off smaller than our goal. Remember, the equilibrium constant is always the goal of what I'm trying to get to. So I put down here that the initial QC was smaller than the KC. So what that means is, just like we talked about on the previous page, in order to get that Q bigger, I needed a shift towards the products. If you notice, I decreased my reactants and I increased my products in order to get that ratio bigger. So you could word that in two different ways. You could say either that I'm shifting toward the products, or you could say that the products needed to increase and the reactant concentrations needed to decrease. Now, the next one asks us the same questions except about experiment 3. And if I look at experiment 3, I notice that my QC is at 2.5. My final KC is only 0.21. So this initial QC was way too big. So then I want to think about, well, if this is too big, how do I get it smaller in order to equal that 0.21? Well, to get that smaller, I'm going to need to increase my reactants, but decrease my products. I need to shift back toward this reactant side. You notice that I took some of these products and basically moved them over to the reactant side. So I wrote down here that the initial QC was larger than KC, so a shift towards the reactant side was needed. And again, in order to get that QC back down smaller, I needed to increase the reactants but decrease the products. All right, I hope you have a good idea now about how we can use the comparison of Q versus K to decide if things are going to shift towards reactants or products overall in that reaction. What do we have to do in order to get to that equilibrium constant ratio? If you have any questions or need any help, please feel free to email me. Bye, guys.